My talk is about the use of digital twin for modeling the network services. I saw that you have yesterday a session regarding digital twin, so maybe I'm going to be redundant, but at least this is our the work that we are doing in the scope of this project. Okay. We have here the definition of digital twin. I guess that all of you knows, but at the end here I put a definition that we work in Ericsson, that the digital twin is not only a software representation of the model that we are working on, but also we enhance that models with capability that are not present in the real network. Okay, and this will be important to understand the results of this project. Okay, network digital twin apply to mobile network. There are a lot of scope and size that we can work on. First is pure site digital twin. This is a very hot topic because allows to manage the sites of the mobile network that we have thousands of them in each of the operator. And for example, in Ericsson, we are working on a physical model of the sites in order to work with them, enhance them, change the technology. Okay, but in this project, what we are going to focus is more in a digital twin of the 5G network in the end-to-end perspective from the RAN, the backhaul, and the user plane and the core of the network. Okay? And for what reason? Well, we want to enhance, as we say, we want to enhance the capabilities that we have in the networks. We already have network controllers that are able to manage the networks, the mobile networks and all the networks. We already have a lot of technology that is able to observe the state of the network. So here with the network digital twin, what we're going to build is a digital model, and we are going to put add-ons on top of this digital model, as for example, using AI-based algorithms that can be trained with the digital twin in order to enhance the physical network. Okay. And here I'm going to show you a very specific use case that we have in our laboratories and are related to the non-public networks. Okay, in the evolution, especially after the introduction of the 5G, the private networks, that basically is to deploy a mobile network, a full mobile network, for example, in an enterprise in order to provide service. These concepts are migrating to non-public networks where we deploy radio and user plane data plane, but the control plane is using this deployment is using the public network as the control plane. So in that we save a lot of management and logistics here because we don't have to deploy a full network, and we only have to deploy only the specific elements that will provide the service to this company. Okay, so we have a big benefit. Okay, because we rid of, for example, of the logistic of the SIM cards and the management of the control plane, but we need to face the fact that for each of these non-public network, we need to tailor the configuration to the specific use case that we're providing. And we must deploy several logical business networks that basically network slices to cope with all the requirements. Okay, and for that we are using the network digital twin for scaling. Okay, because in this schema we will have a lot of non-public networks integrated in the public network, and we need to scale that. We need to automatize the configuration and management on those non-public segments in order to scale. Okay. A practical use case that we are testing in this project is in the Photonic laboratory that we have in Leganés, when we have a 5G network that can be tested for testing different business cases. Okay. And here is the problem that we have. We started with one non-public network, portable system with the radio elements, the transport elements, and the user plane. And now we have a lot of them. And we have a lot of them across not only here in Madrid, but also deployed in other laboratories, like the CTTC and I2CAT in Barcelona, and also in 4 premises in the engine manufacturer premises of Ford. So we have some segments of the network that are deployed in environments that we don't control. Okay, and how we deal with that? Using the digital twin. What we have here in Photonic is a digital twin of each of the non-public segments that we have across the Spain. Okay, and for what? Well, stop working. Okay. Seems to be incomplete, Antonio. Que no avanza. Ahora. Sorry for that. Okay. And for that, and for using this digital twin, what we are doing is monitoring the deployments that we have, and using a closed feedback loop, we control them. Okay. This is the architecture of the network digital twin that we are using. Not important, but those are the basic use cases that we're implementing with the network digital twin. The most important one is the intent-based configuration. Basically, we have the requirements of our business use cases, and based on that, we propose a configuration of the non-public segment. Okay, the configuration includes not only the radio parameters that we can modify, for example, the spectrum band that we are using, the bandwidth, the power of antennas, but also more complex configuration, like for example, the use of network slicing. Okay. Using the network digital twin, what we can do is monitoring the current performance of the network, but we can also predict the future network performance on the network based on the use that the customers declare. Okay, and with that we can do a kind of performance checking, let's say, of the non-public network. Okay, but this is just for automating the deployment of the non-public networks, and we are working on more advanced use cases, like for example, to use the information that we have in the digital twin in order to train some artificial intelligent agents. In this example, for example, we implement a feature that is called hold and forward, that is part of the TSN support in 5G, that basically is the jitter of the traffic. Okay, we have in this project, in this use case, a big requirement about being strict in the jitter that we are introducing in the use case, and using the fact that we can simulate the behavior of the network, we can train this agent and we can dejitter the traffic. So basically, we have a constant latency in the output of the system. Okay, and this is the last enhancement that we introduce in our system, that is basically to create a generic smart dejittering that, based on the modeling that we have of the non-public network, we're able to dejitter any traffic without knowing it. Okay, because in the previous one, we knew that this is a kind of control protocol, is periodic, is easy to dejitter. In this one, we are able to, using this information, to train an agent that per packet is able to decide the buffering time of each of the packet, and we are able to dejitter the packet. Okay, it's pending publication, so I don't include too much details.
It's recorded.
So basically, what we are working on this is that obviously network digital twins is a powerful tool for network management. We are able to full automate the non-public segments of the network. That is good because this allows us to scale, but is also a very powerful, a wonderful tool in order to enhance the model introducing these A-based algorithms. Okay, and that's just for my side. Thank you. Yes, please.
Why only for
Sorry?
why only for events?
Why? Well, what we intend here is to apply the jittering with the current technology. Okay, the hold down forward, as is specified in the standard, is basically a model that you define a packet delay budget of your network, and then you measure the time that your packet is in your system. Well, how? I don't know, marking, time stamping the packet. You need to use layer 2 time stamping, layer 2 IP Ethernet PDU sessions, or try to time stamp the packet in a transport level. TCP is easy, in UDP it's not so easy, okay? But this requires, for example, PDU of type Ethernet, and we don't have commercial UIs that support that. So what we try here is to implement the jitter using the current state of art in 5G. And that is, and for that, we use IP-based flows. Okay.
Okay, and this is done in the UP.
This is done in the UPF. For the uplink, in the network translator, in the downlink is in the device side translator, in the output of the network. Okay.
Okay, thank you.
Thank you.